Hi everyone, welcome to Year 9 Physics. Not the ideal start to Year 9 Physics, but we intended always to start GCSE Physics in January of Year 9, and so that's what we're going to do. We're not going to start off with a kind of topic as such. There's a specification for GCSE Physics, and in it there's a kind of like a list of all the topics and the kind of physics stuff that we'll be covering. But aside from that, there's also a separate list, a working scientifically kind of section, with some math skills in it, and that kind of underpins the whole course. So just to make sure that we're doing our maths and laying out our numbers properly, then we're going to be doing this units and prefixes first, and then we'll be coming back to it regularly, so that we don't kind of forget how to do these things. So starting off with units, we've got this weatherman. He's saying it's warm outside. I mean, clearly it's not warm. It's like a snowy background, isn't it, in this little animation? So he's probably come from somewhere that's really, really cold, and then he's gone to this place that's slightly cold, and so he's saying that it's warm. But if we went there, we'd be saying it was really cold. So it's not useful for the weatherman to say it's warm or it's cold. What we want the weather people to say is it's -4 degrees or 10 degrees Celsius. So you notice that a number and then add a unit. Now, in shorthand, you might just say 10 degrees, but when we say 10 degrees, we mean 10 degrees Celsius. And so we've got that number kind of means something. In a similar way, if we've got an example here about a dog daycare centre. If someone asks the manager of the dog daycare centre, how much does it cost? What are your pricings? And she might respond with, sure, we charge $150 for 4 or $225 for 8. Now this is completely meaningless. We don't know what she's talking about. She's talking about money. Is she talking about hours? Is she talking about the number of dogs? We don't know what those numbers mean, and so she might as well have not said anything. It's useless, more confusing, if anything. So we need to make sure that our numbers have got a unit. So the system of units that we use in physics is called the International System of Units, or SI units for short. And we need to make sure that we're using units from this kind of system of units. If we start using miles, pounds and ounces, when we start to use formulas and multiply these things together, divide them, we're going to end up with really complicated unit systems that don't really make any sense. There are other unit systems apart from the SI units, or the International System of Units, but we're using in physics at the moment the International System of Units. A couple of hundred years ago, they used the gram centimetre second system of units, which is kind of similar, but we don't use that anymore. Before that, maybe we used it maybe an imperial system of units. But at the moment in physics, every physicist uses these unit systems, which means that physics around the world, our numbers are comparable. Right? If you measure, I don't know what, the speed of light in Switzerland, you measure the speed of light in America, you end up with the same kind of number because every physicist is using the same units. So this isn't all the units in the International System of Units, but they're kind of important ones. There are some that we're going to use that aren't on this list. But what I'd like you to do is fill out the table. I don't really mind how you do that. Print it out, draw it out. I don't really mind, although don't spend ages trying to make it look neat in your exercise book, because by the time you're in year 11, you're not going to have that exercise book anymore, chances are, and you're just going to revise from a revision guide. So do it as quickly as you can, but fill out the table, use the internet if you need to, but pause the video and get this table filled out, please. Thank you. Okay, so hopefully we were able to find out that the kilogram is the unit for mass. The quantity is mass here. This is the odd one out of the whole list. This is the only one that's got kilo in front of it, or really anything in front of it. So I guess you can have milligrams, you can have centigrams, you can have grams, you can have kilograms, you can have megagrams. But the kilogram is the standard unit of mass. All of the other ones in this list don't have a prefix like that, right? So you'd think, oh, it should just be the gram. And it does annoy me that it's not just the gram. But because of historical, the way that the units have been derived over time, unfortunately, we're stuck with the kilogram being the standard unit of mass. And if you want to know why, you can ask why we use the kilogram, not the gram. You can ask me, or you can look it up. I'm sure you find it online. It's kind of interesting, but I'm trying to keep this video short so that everybody manages to watch it and do the work, obviously. It's not part of the course, but if you want to find out, I'll tell you. Just try and remember that that's the only one with the prefix. Distance is measured in meters, and the unit symbol is a lowercase m. Now, these cases, they do actually matter. If we do a capital M, it is wrong. Having said that, an examiner's probably not going to be able to know if your handwriting is not perfect, which whose is. They might not notice you doing a capital M, and you might get away with it. But you need to make sure that you're trying to use the right case, and some of these really do matter. Time is measured in seconds, and the unit is a lowercase s. So again, if you've drawn what could be confused with a capital S, please put a cross next to it and write a lowercase s. It should be lowercase s for seconds. The kind of rule is, if it's named after somebody, it's a capital, and if it's not, then it's a lowercase. So there wasn't a Mr. Second at some point, but there was a Mr. Joule. So James Joule, famous physicist from the past Victorian times. So we need a capital J for joules. Now, the font on this PowerPoint slide is not the best. Really, what I want from you guys is a bar across the top of your J to make sure that it's really obvious that it's a capital J. But definitely we don't want a little dot, because then that's saying it's lowercase, and it will be marked as wrong. You don't lose a mark for something like that. It's daft. Power. We measure power in watts, and the symbol is a capital W because James Watt was a person again. Hopefully you managed to find that out. Potential difference, we measure that in volts. The symbol is a capital V because Voltaire was a person. Ampere, again, person, so it's capital A, and that is the unit, the amp is the unit for current. You will have covered that already in the electricity modules that you've done previously, but it is something that is, I guess, a fairly easy one to forget because we don't use the word current and we don't talk about electricity in kind of everyday life so much as some of the other things like energy and distance and so on. So, but anyway, it is current, and of course you could have looked it up. And last one, coulomb is the unit for charge, and again that is something that you could have looked up. Unit is a capital C for coulombs as well. Let's make sure that we kind of know that one. Good. So these are our standard units. There are more standard units that aren't on this list, but these are kind of some of the main ones. Okay, so we've got our units, but now if I've got a really large number, so let's say I want to say how much energy a power station will put out in a year. That's going to be a huge, huge number of joules, and if I'm trying to write out 0, 0, 0, 0, 0, 0, 0, it's going to cause me problems. I'm going to miss out some zeros and get it wrong. It's going to take a lot of time, which is not time I want to spend in my exam. And so we've got these things in physics. We've got these prefixes, which mean that we don't have to write out all the zeros. But of course, that can then be confusing, because if I've got kilometers and I want to find out a speed in meters per second, I'm going to have to convert that kilometers into meters before I start doing anything else. So I need to be able to convert the units that you might get given in a question into those standard units that we had on the previous slide. And the way I'm going to show you to do that is by using standard form. Now, you've done this, we've done this before, not standard form, but converting units. If I told you to convert, 25 kilometers into meters, then most of you would be able to do it. You'd say, oh, I know how to do this. There's 1,000 meters in a kilometer, so I'm going to times it by 1,000 and I'll end up with 25,000. Great, that's right, there's nothing wrong with that. But when we get to 25 gigameters, then it becomes more complicated. So, or maybe 25 nanometers. So millimeters, you divide it by 1,000. Okay, good. Micrometers, you divide it by 1,000 twice. Well, that's something that, again, I've now got to remember. I've got to divide it by 1,000 and then divide it by 1,000 again. Nanometers, got to divide it by 1,000 3 times. And you think, well, how many times have I divided by 1,000? Have I forgotten to divide it by 1,000? Do I divide it by 1,000 4 times? It's complicated, and I've been doing this a long time. The best way of doing of converting these units is by using standard form, and also standard form is on the specification, so we have to know it anyway. So we might as well just make sure that whenever we convert units, we just use standard form. It's easier, as long as we can remember the stuff that's in this table. Now, the way we're going to remember this is just going to use this table really, really often. So what I'd like you to do, if you've got a printer, I'd like you to print out this table and stick it on the inside of the front cover of your exercise book. And that's what I'd do if we were teaching in real life. Or you can draw it out. Or if you think, actually, online lessons, I'm not really using an exercise book, I don't mind. It's your exercise book, you can write in it or not write in it. As long as you're obviously doing the physics and learning the physics. It's what's up here that counts at the end of the day. And you can use a revision guide, so that's fine. But you're going to need this table, so maybe take a photo of it on your phone and you can refer back to it. Take a screenshot of it and put it on the desktop. I don't know, but make sure that in the subsequent lessons for physics, you've got access to this table in like seconds, so that we're not wasting our time. We're going to start using this table now. So if you could get some scrap paper, back of your exercise book, mini whiteboard in your planners and a whiteboard pen. You don't need to keep these answers, but you're going to need somewhere to write something for this task. And I'd like you to write down 12 kilometres in metres, but before you do, I'm just going to say the way I'd like you to do this is to swap the K with the value from the table. If you haven't quite grasped what I mean by that, then you can do it in the way that you would have done it before this lesson. And you'll see when I come up with the answers, the kind of way that I'm intending for you to do it. So, pause the video and write down 12 kilometres in metres, please. Great, so Mr. Bates wrote down 12 times 10 to the power of 3 metres, which is the way that I asked you to write it down. But you might not be comfortable with that, because in maths, when you were taught standard form, you were taught never to do that. In maths, what you have to do is you have to write down 1.2 times 10 to the power of 4 metres, which is also correct, but it's an extra step that we don't really need in science. You don't need to do that in science. This is a special type of standard form. It's called engineer's standard form. And what we do in standard form, engineer's standard form, is we make the power a multiple of 3 deliberately, because if you look at this table, all of these magnitudes are multiples of 3, the powers. So we've done it on purpose so that we can just swap between the two, between the prefix and the magnitude. So, and Mr. Bates will have fewer problems the way he's done it, with larger and smaller numbers. Miss McLaughlin has written 12,000 metres. That's also correct. So there's kind of 3 right answers. You can have 12 times 10 to the power of 3, 1.2 times 10 to the power of 4, or 12,000 metres. All of those answers are correct, but the way that Mr. Bates done it is going to set him up for the rest of the questions rather well. Okay, we're going to do 12 millimetres now, so pause the video. 12 millimetres in metres, please. So we can see Mr. Bates again, 12 times 10 to the power of minus 3 metres. If you wanted to, you could put that into kind of proper maths standard form, and you could write 1.2 times 10 to the power of 2 metres. This, I think, highlights the kind of problem with doing that, because some of you would have tried to do that and done it wrong and ended up with 1.2 times 10 to the power of minus 4 metres, which is wrong. So there's no need to get it into maths standard form. Please just use engineer standard form. We're trying to reduce the opportunity for getting it wrong. You don't need to put it into maths standard form, but it would be technically correct to write 12 times 10 to the power of minus 2, 1.2 times 10 to the power of minus 2 metres. But there's room for mistakes because you can go the wrong way quite easily. And Miss McLaughlin's divided 12 by 1,000 and ended up with 0.012, which is maybe how you've been taught to convert millimetres into metres in the past, but now we know how to use engineer standard form. We're hopefully going to write down 12 times 10 to the power of minus 3, especially when we get to even smaller numbers. That'll make it even clearer. Okay, next one. Next one is 24 megajoules in joules, please. So pause the video and have a go at that. Okay, so we can see Mr. Bates has gone for 24 times 10 to the power of 6 joules, which looks correct, but actually he's gone for a lowercase j, and James Joule was a person, and so he's got it wrong. But the number element is correct, but the unit is wrong, so it's actually wrong, Mr. Bates' answer. Sorry, Mr. Bates. Miss McLaughlin has started to use standard form, but she's gone for math standard form straight in, and 2.4 times 10 to the power of 7 joules with a capital J. That is correct. There's nothing wrong with that one, so it's correct, but it's an unnecessary step. Right, 80 micrometers in meters. Okay, so 80 micrometers in meters, 80 times 10 to the power of minus 6 meters from Mr. Bates, great. that's what we're expecting. It's a lot easier, isn't it, to just look up in the table in the grid what the size is and just write it down, just swap that mu, that micro symbol, for times 10 to the power of minus 6. Much easier than dividing it by 1,000 twice, which means you're going to end up with some mistakes there. Miss McLaughlin's tried to go for math standard form again and ended up with 8.0 times 10 to the power of minus 7. She's gone the wrong way. It should be 8.0 times 10 to the power of minus 5. So this is what I'm saying. Don't try and overcomplicate things. Literally just swap the prefix for the size or the magnitude in the table. Okay, so last one. I'd like 150 gigawatts in watts. So pause the video, and 150 gigawatts in watts, please. Okay, so Mr. Bates, 150 times 10 to the power of 9 and a capital W for watts. Perfect answer. Ms. McLaughlin has gone back to writing out the full number. And this is an issue that you can have. It wouldn't be wrong if she'd written enough zeros, but she's actually only written, she's done 1, 5 and then 9 zeros, and she should have done 1, 5, 0 and then 9 zeros. And so she's just copied the number from her calculator onto the whiteboard. She's copied it badly. That happens to people in exams all the time. And if you don't copy it in the first place, if you just write it in standard form, or an engineer standard form, then you don't have that problem. So please just swap the prefix for the magnitude or for the size, because it makes things easier. There's no need to do anything different. Okay, so hopefully we feel more comfortable with that. We kind of know what I'm talking about with engineer standard form. I'd like you to convert all of the values into standard units for me, and then that's what I'd like you to turn in. Just make sure that when you're doing the ones with time, so seconds is 60 seconds in a minute, you can't use this engineer standard form with that. You have to times and divide by 60. Sorry about that. And similarly with the mass, you've got to remember that the kilogram is the standard unit of mass. So we're trying to get everything into kilograms. And so actually for mass, you might want to use numbers rather than using the engineer standard form. You might want to just use straight numbers. And so you might say, instead of saying 1 megagram, that's not what we do really. In physics, we try and convert everything. So we would say 1,000 kilograms, and we just use the number rather than the engineer standard form. But give these a go. Hopefully you've learned how to convert units into standard units. And at the start of every calculation question, you need to make sure that your units are standard units. Otherwise, you're going to get the answer wrong. Okay, so good luck with this, and we'll start the proper content next lesson. Thank you.